Hello. Hello. Can someone at the back help to close the door? Close the door at the back. Okay. Welcome back to Discrete Math. Some announcement. So there's this math help center that you can attend if you can't meet me in the office hour or appointment. It's Tuesday, Wednesday, Thursday, Friday, 2 to 4 p.m. There will be postgrad student there to be able to help you. Okay. I think it'll be announced in the Teams or somewhere, not sure. In the math group as well. Before the Q&A section, I want to clarify something from last week. So last week, there's a student asked about this PXOR, QXOR. So typically, first you should tell people which to do first. So either PSOR Q first or QSOR R first. Okay. And what I said last week, I said the wrong rule. It's not this one. So it's the associativity rules, which we will go through again today. So associativity rule helps you to identify these two identity. In fact, if you do the truth table, they are the same. So actually, it doesn't matter which bracket to do first. Okay, so in this case only, so there's no ambiguity of doing P X or Q X or Y. But to show there's no ambiguity, you need to prove it first. Okay, this is the associativity rule. And also, there's a student come to me after the first hour asking me, if P true, Q true, why is it true? Or maybe if P false, Q true, why is it true? So when I say true here, there's no connection. I didn't mention any connection between these two statements. Okay, this is something you need to prove. This is some what need to be done. When I say true here, it just say that this statement is valid. Okay. For example, okay. For example, true implies false is false. Then what do you mean by false here? Okay. So what it means here is true cannot imply false. Okay. So this statement, the whole statement is false. For example, okay. For example, so let's say I say that if P then Q, that means if I have P, then I must have Q. Okay. But if I have P, but Q is false, so I don't have Q. So this statement doesn't work. Okay, this is what the false means here. Okay. Confused? I see some confused faces. Any question? Okay, I open to question. Open to questions. Yes. Say again. What's your question?
Why I don't have P, but I have Q?
If you don't have P, but you have Q. You mean this false implies true? So false implies true is true. You know why? You know why? Because, okay, let's say you say that, okay, if P happen, then Q must happen. Okay, but in this case here, in this case, so P false, so it doesn't happen. Okay, but Q still happen. So why is this statement true? Because Q might happen due to other things, maybe due to R, not necessarily due to P. So this statement still hold. Okay. Make sense or not? So yeah. So even though you say this, but this doesn't happen, P doesn't happen, but Q happen, uh it may be due to other things. So this statement itself still valid. Any questions? Any other questions? Any more questions? So maybe some another, not to complain, but some say that maybe the way of teaching is very fast, but they say that it's a university style. So I urge you um to adapt yourself to this kind of studies, and then see if the pace is also still too fast, then you can let me know again. Okay. So because this is not like the high school, you have one subject have how many hours? Maybe 2 out of 5 days you have the same subjects, but in uni you only have 3 hours per week. Okay. So I understand your situation because I'm also once a university student not long ago. So I provide you a lot of references. So you can go through the references, go through the examples, and then go through the previous year lecture notes. See if you can do it or not. So I try to avoid the same question they use. So after you look at my examples, try the PDF file I put on the Moodle, the previous year lecture notes. Try the example, see if you can do it or not. If you can't do it, you try it, and then you come to my office hour. Okay. So my office hour is 12 to 4 today. Okay. And there's no one from 12 to 2 today. So make sure you make full use of my office hour. And then I made an announcement is about the mid-sem. So mid-sem is when 3:30 to 5:30 instead of 3 to 5. And then I will confirm it this week probably if there's no other adjustment. Any more question? No? Then we jump into today's topic. Okay, we will do some revision. So last week we talked about this tautology, right? So tautology is a compound proposition that is always true. Contradiction is a compound proposition that is always false. And then I make these two examples. Okay. And did I do this last week or not? Did I do in this class? Yes or no? Yeah, okay. So I just recall. So for example, to prove that P or not P is a tautology, so you do a truth table, and then you will see that the compound proposition is always true. And then similarly, if you do it for contradiction, and then you will see that P and not P is always false. Okay? Sure. So today I will go into something called the logical equivalence that I promised you last time. Okay. So let's see. So what's logically equivalence? So logically equivalence is an adjective, okay? So what is it for? It is for two compound proposition. Okay, first of all, you need to start with two compound proposition. And then you want to show that something is logically equivalent if P, if and only if Q is a tautology. Okay, so this is what you need to check. So I have told you what is if and only if, right? I also told you what is a tautology. Okay. So actually, there's an easier way to check something is logically equivalent. So P and Q are logically equivalent if they have the same truth values in all possible cases. Okay. Okay, one exercise you can do is to show that uh, exercise show these definitions are equivalent. Okay, make sure you do it. If we got time, maybe we can come back, but for now, I want to jump to example first. Okay, so for example, show that not P or Q and not P. Okay, I introduced the notation maybe easier. So this is the logically equivalent notation. Logically equivalent. Show that not P or Q is logically equivalent to not P and not Q. Okay, do you know how to do that? Huh? What's the definition of logically equivalent? Huh? Yep. It's the same. What do you mean?
Not P or not Q.
It's not the same or it's the same? Yeah, it's not the same. Never mind. It's fine. Wait, where you get the? You mean the knocks? Is it? Where you get the question from? Oh, Moodle one, huh? Yeah, yeah, that one is from previous year. This one I do. Yeah, yeah, yeah. Yeah. This is the example I picked. Maybe it's different from the knocks one. Most probably it's different from the knocks one. Like what I said just now, I try to avoid so you can see different examples. Yeah, try do this one. This is the other one. Okay, so how to show? How to show something is logically equivalent? What's the definition? Can anyone tell me? They have the same truth values. Okay, so show that they have the same truth values, or show that P if and only Q is a tautology. So what is P if and only if Q in this case? Can someone tell me? Ah, okay, so show that P if and only if Q is a tautology. Can anyone tell me what is in this case is? Hmm? Blur already. Huh? Blur already. If no one answering me, then I pick name or who is Liu Xing? Is Liu Xing here? No. Who is Liu Xing? Liu Xing? Hello? Liu Xing not here? Liu Xing's not here? Liu Xing? No? Han Xingyu. Han Xingyu. Who is Han Xingyu? What? Hey, sleepy, huh? Sleeping. Who is Han Xingyu? Huh? Hello? Okay. Don't want to call name. Okay, I just pick. Yeah, you. Yeah, try. Okay, so my first question is how to show that these two compound proposition are is a tautology. Oh, sorry, are logically equivalent. You want to draw it on blackboard. Uh, can you tell me using the definition first? Hmm. Huh? You can't describe it. I you okay, I'll let you draw first. I'll let you draw. I'll let you draw.
I define two.
Yeah.
Two is hello one.
Consider.
I define two is one.
Okay.
Four zero. First, P. They're also right.
Yeah.
Also right. And, also they are same constant. Same. To me, that's it. And they are all there. You also, I don't know which one. Also.
Done. Done.
Done.
Okay. Okay. Um. See. So you want to send that I can see. Oh. Okay. So what do you get? So okay. So he defined true is one, false is zero. Okay. Use the Boolean language, right? 1 0. That's where you done it. So P, Q, okay, all the combination, 2 times 2 for them. And then C, this is parallel. P of Q, P of Q time. Okay, this is one. Okay. This is another one. Okay, let's check. So P of Q is 1, not 1, 0, 1, not 1, 0, 1, not 1, 0. Okay, 0. That's okay. Wait. Huh? What? This one is what? Yeah. 1. They say 1 on this one. Now let's check. So 0, 0, 0, not 0, 1. So this is 1. Okay, this is 1. Okay, and then this one, not P 0, 0, and 0, and 0, 0, and not P 0, 0, 1, 0, and 1, 0. So 1, 0, 1, and 0, 0. And then 1 and 1, 1. Okay. So why this one? For 9 is for never mind. Never mind, just say. Just say. Why is this done? Okay, so the question is, why is this done? Huh? You don't know. So how you come up with this answer? Okay, thank you. What's your name? Huh? Okay, okay. Yeah, so why is this done? So from here, to show that P and Q are logically equivalent if they have the same true value in all possible cases. Okay, so in all possible cases, you have the same true values. Or you can show that P if and only if Q is a tautology. See, I show here. This statement if and only if the other statement is all true. Okay? Okay. Okay, very good. So next, so actually there's a name for this. So this is called there's a famous law called the De Morgan's law. You must know this every De Morgan's. Okay, De Morgan's law. Every logic student must know this. Okay. After you know this, you can call yourself a logic student. Um. Okay, the other one, as somehow pointed out in the note, I think is this one. This is the pair of the other pair of this De Morgan's law. So these two are all De Morgan's law. So you can notice that not go into the or, you become a n. Okay, you not on both, and then or become n, and then n become or. Okay, this is a good exercise you can do exercise. Okay, go back to do this. Okay, so that not P and Q is logically equivalent to not P or not Q. Okay, any question? Any question? No question? Please don't sleep. Make sure yourself don't sleep. Do something. Because my 9 o'clock to 12 p.m. one also got people sleeping. They say too early. If this is too late, then every time can sleep already. Okay. Next, do something. Make sure you don't sleep. Okay. Otherwise, I'll call you out. Okay. Next. So let's see this. We got a lot of law here. Okay, let's see. I can move things away. not good. Okay, let's see. Let me move this from here, and then this one. Okay, there's a lot of law here. Maybe you will get shocked, but anyway, I will explain a little bit. So shouldn't get too how to say, too what's the word? Huh? First of all, you don't need to memorize this. If I want you to use it, maybe I will provide you, but I won't tell you how to use it. And second, you should understand this table here. Okay. Actually, these are very usual operation in algebra. Okay. So if you think of these O as a plus and then N as a multiplication, actually in the number system, you already know that. For example, if you take any number and then you add it with a zero, you get it back itself. And also, if you take a number multiplied by one, you get two. Okay. So this is what the identities law here do. Okay. So if you take a proposition and then end it with a true statement. So this T here is a true statement. Okay. You will always get back P. Okay. And similarly, if you take P and then disjunction with a false statement, you will always get P. Okay. You should show this logically equivalence by using what? By using what? Huh? How to show logically equivalence? Truth table. Okay. So use this kind of method. So replace the P and T here and then P here. Okay. Right. So similarly for these other, so domination laws tells what? Tells you what? So if you this true statement will dominate the P. So you only get true statement. If you put P conjunction with F, then you get at the false statement. Idempotence law. So idempotence is a things that square. Wait, let me change. It's a thing that square to itself. Okay, so you see, so P or P get back yourself. P and P get back yourself. Okay, this is the idempotent. So double negation law, actually I used it last week. I didn't show you whether it's true or not, but now you can show it using this. Okay, I think there's one tutorial question this week on this. And then double negation law is like number system minus minus one is one. Okay, commutativity's law. So like what 2 plus 3 equals to 3 plus 2. Okay, commute. And then associativity laws is what I tell you just now. So you can do PQ first and then do QR and then do everything, or you do QR first and then do everything. Okay, associative. Distributive is you sort. Okay, you see? N all first and then N, or N first and then all both sides. So it's like, you see, like the open bracket thing. But make sure you do the right order. Okay. Similarly, and then the Morgan's law is the one we did just now. Absorption law meaning P or P and Q is P. So so actually this is a bit interesting. So why is it interesting? So let me give you an example here. I think of one example. So let's say there's a thing that both of us have to be there, okay? So I have to be there as P, or I have to be there and you have to be there to do the things. Actually, in logic, you don't have to be there. Just need me to be there. Okay, it's just P. Okay, you are not important actually. Okay, Also, if I change the question to be, I have to be there and I have to be there or you need to be there. You think that maybe you need to be there, but actually you don't need to be there. Actually, I have to be there. Yeah. So this is the absorption laws. This is very important for shortening the proposition or shortening the condition. So if you write coding, right, there's a lot of condition you need to consider. Maybe you jump into this kind of situation. You got this P, and then maybe you have another Q again, but it's an O or N and O. Actually, you don't need Q in your coding. So typically coding will jump into very long chunk if you don't know how to write. Like you want to put a lot of things in. Actually, um, you may simplify your code sometimes. Okay, using this logic. Okay, the more thing you put into, the more bug you will get. Okay, later we will prove. We will do proving. So to see whether how to prove something works for different cases. Okay, and then negation law. I think this one we did before, right? So which one is tautology? Which one is a contradiction? Okay, this is what we did last week. Okay. Okay, next is this one. Okay, this is very, very important. Not all of them, but at least two of them you need to know. Okay. So first is this. P implies Q is actually not P or Q. Okay. Should do this exercise. Okay, maybe we'll do it later. So notice that I didn't tell you what is not P implies Q last week. I didn't tell you what's the negation of this last week. Okay. But once you know that P implies Q is not P or Q, then the negation will become easier. Okay. So the negation is actually, if I you see, so I will show you how to use the previous page. Okay. So let's say we have this line here, and then I want to negate P implies Q. So negation go into the or. What laws I need to use? D what? I give you a hint. What law? D what law? What laws? If you want to negate the disjunction, what law you need to use? D Morgan's law. Okay, that's the only one law I want you to memorize today. So D Morgan's law. So I will have not P and not Q, and then not P is what? P by the double negation law. You see, you didn't memorize. Did you memorize the law? You didn't, right? But you know how to use. Okay. Yeah, this is how it goes. Okay. So P and Q. So not P implies Q, meaning you got P, but not Q. Okay. So this is how you negate this. P implies Q. Okay. So if you want to show that P implies Q is wrong, you need to come up with an example. You have P, but I have no Q. Okay, this is how you prove P implies Q is wrong. Okay, another thing I already told you last week. This is the what you should recognize this. What's this? Swap and then minus minus. What's this? Huh? Converse, contrapositive, or inverse? Which one? Huh? Say again. Say again. Contrapositive. Okay, so this is the contrapositive. So you need to show okay, we will do it later. Okay, we do it later. And then the others are all derived from these two. Okay, the others should be able to derive from these two. Okay, so go back and try. Maybe I put some into the tutorial. And then also this one is very interesting as well. So I also said it last time. P if and only if Q actually is the combine of these two. Okay. So now you can show it rigorously using this method. Yeah. Okay. Using the tautology method. And then the other are the derivation. Okay. Derivation. You should try it. Try. Try it at your free time. Okay. Let's do what? Example. Okay. Show that P implies Q if and is logically equivalent to this. Has someone done this yet? Anyone done this? Anyone done this? Who want to show it on the board or not? You want to try? Huh? Try. You do it on this board. Yeah. Try. Okay. Who? Uh, is there any second one want to do this? Show that P implies Q if only if not Q implies P. Huh? Any breath part? You want to try this? Mhm. Maybe I read that somewhere. Okay. But, yeah. Huh? You done? Okay. Okay. Done? Okay. Yep. Okay. Let us see. Excuse me. Okay. So what we want to show P implies Q is logically equivalent to not P or Q. So true, false, true, true. Yes. Okay. So you say that there's a true, same true value. Anyone? Any question? No. Next. So this question, okay, first you can show using the truth diagram. That's fine. Also, if you already know that know the other logical equivalence, then you can use the algebra method. So first, I already proved that these two are equivalent, so I can do this. Second, I know that all is commutative, so I can swap. After I swap, I use the same previous logical equivalence and then I turn it back to the implication. Okay. So yeah. So this is the make sense? Okay. So first is the so you can try first you can try the truth table method. Second, you can try the algebra method. Okay. Both method you can use. Okay. Any question or not? Huh? No question. Should we do one more or we go to the next one? You want to do one more or we go to the next topic? Depend on you. Okay. So I give you exercise first, and then if you want to do, then we can do. If no, then we jump to the next one. So this is the third exercise. Exercise. So you want to do yourself? Then I go to the next chapter. Is that okay? Huh? You do yourself? Do yourself? Okay. And then you can chill with me. No complaint, huh? Go to the next chapter. Yeah, let's go. So the next chapter is quantifier. Okay. Okay, now things get a bit interesting now. Okay. So quantifier. So we want to add function. We want to consider different things in one proposition. Okay. So sometimes you call it a predicate logic or quantification logic, quantification logic. So let's see. So okay, so typically we got a sentence with a variable x. Okay, I think last time we already encountered this kind of sentence in the tutorial, right? We can't decide whether it's correct or wrong. That's because we haven't give it a domain. Yeah, let's see what the domain is. So we will call P itself a predicate and X a subject. Okay, if Px contain these two P and X is a proposition. Okay, but it's not proposition when X is not specified. So we have to specify X as well. Remember the tutorial question we did last week? And the set, okay, actually, sorry, this set I haven't defined yet. I can't define it now as well. You have to wait until second topic. So sometime they introduce set theory before logic. Some book do set theory first, then yeah. So you have to start somewhere. So we start with logic. So for now, set is a collection of object. Okay, collection of object. So the set of X lives in is called the domain or the domain of discourse. Domain D. Okay, so the set you can think of it as a space. Okay, like this room. So you are in the set of discrete map. Okay, every single one of you is in the set of a discrete map. Okay, you can think of it as a space for now. Okay, so example, e.g. So suppose x is in integer. So this, okay, later I will further introduce this. Let's call it integers now. X greater than 0. Okay. So my px here is what? Is x greater than equal to 0. Okay. So this is the predicate. This is the subject. Okay. Right. So it says that, okay, this itself, remember last time we said this is not a true, not a proposition, because we can't decide it's true or false. Okay. But if you put p x equal to 1, what do you get? 1 is greater or equal to 0. True or false? True or false? True. But if I put p minus 1, minus 1 is greater or equal to 0. True or false? True or false? False. False, right? Okay. Yeah. Any question? Is it confusing or not? Okay. So, of course, let me right here. So, outside. So, if I only have one variable, we usually call it a one. Maybe we don't call it one array, we call it single array. But if we have more things that we can substitute, maybe up to n, then we'll call it n array predicate. Okay, this is just some notation. So, like the simultaneous equation, you got two variables, something like that. Okay, and then there's some example of domain I want you to know, so that we have some common language to speak about. So I want to quickly introduce you the number system. Okay. First of all, is the natural number. So some convention they count natural number from 1. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. Because they say that the 0 doesn't exist. So when you do counting, of course you start from 1. But there's also another construction of natural number using the piano axiom if you want to find piano axiom. They start with 0. So they start with an empty set. So maybe I just include 0 in here. Okay. Also, if you want to do, okay, never mind. So so our natural number start from 0. Sometimes they will write like this, n greater or equal to 0, to state that including 0. Sometimes. Okay. Second is the integers. Okay. So integers are the one that are the negative number and also the original one. Okay. So why are there a negative number in here? So when you add the numbers here, right, you only get bigger, bigger, and bigger and bigger. And the 0 here, like what I mentioned just now, is a identity. So every guy at 0, you get back itself. But is there anything that add to a positive number you get back 0? Is the negative number. So that's why we introduce this integer number here. Okay. And then next we got the rational number. Okay, rational numbers. Rational numbers. Now, rational numbers are what? Are the fraction. So they can be written as m over n, where m, n are in the integer. Okay, for example, you will have negative 7 over 8, minus 1, 0, and so on. Also, you got 4, so on. Okay. Okay. There's a bug here. There's a bug here. So actually, I didn't introduce what are these. So you just study it at it is first. And then when we go into chapter 2, then you will know what are these. So for now, you just think that these number are the example of number of here. And then this is the bracket. Yeah, bracket. And then if you see this and then slash usually give the condition on this guy. So when I talk about this, and then I have to tell you what is mn. So slash mn have to live in z. And then n cannot be 0. Okay. So because divide by 0, you got something undefined. Yeah, it's another story. Okay. And then you should know about the irrational number. You know about irrational number? So these are the number that cannot be numbers that cannot be expressed as ratio of two integers. Okay. So for example, you have pi e square root 2, so on. Okay. So when you do the decimal expansion, the pattern doesn't repeat. So you can't write it in this form. Okay. And then you should know that the real numbers are, uh, are all these numbers. Okay. Okay, I didn't introduce this notation, right? So this is union. So when I say union, it's like take all of them together. Okay. For now, what I want you to know is what are the number, what kind of number is in N, what kind of number is in Z, what kind of number is in Q, what kind of number is in R. Okay, I don't need you to write down this thing, but I need you to know what kind of number appears in this guy. Okay. Similarly, this notation will get even more clearer after chapter 2. Yeah, which is next week. And 6, I think you also encounter something called complex number, but maybe we will do less, maybe appear in the exam, I don't know. But I introduce here first. So r plus r I at I square equals 2 minus 1. Okay, maybe there's something like this, 3 also in there, so on. Okay, yeah. Yeah, this is the example of domain. So maybe I have a positive integer. You know what's the positive integers? So they are all greater than 0. Negative integer are those less than 0. Non-positive integer, they are all number greater or equal 0, include 0. Okay. Also can have non-negative integer. Non-negative integer. Wait, am I doing something wrong? Non-positive. Okay, non-positive is less than equal to 0. Right. So not positive, non-positive. Okay. Non-negative, not not negative. So it's okay. Is it clear? Okay. Any question? No. Okay, I think we should take a break here. Okay, we take a break and then come back at 5:05. 5:04.
我有一个想法，
Yeah.
就是那个之前讲那个，就是这个，就是可以画出来。这个是 P，然后这个是 Q，然后 P and Q 的 P O Q 就是这样子，然后非 P 就是这个，非 P 就是这一块，这一块就是非 P，然后这样的话来做这个是不是也是可以
？If you want to do, if you want to try this method, yeah, okay, you need to show it for every. I mean, I think someone has. So you need to make sure that every theory what you observe here, right, is just observing that this is P, this is Q, right? So and then what do you say? So this is
P and Q，
this is P and Q.
对。
Okay, so what you observe now is you observe that actually this is set theory, right? So
他说中
P
文我不听的不是特别
听不懂，
不是特别懂。
可能学一下，学习一下，
学习。
对对对，
这
所以我说慢一点
啊。
Okay, so okay, so what you observe, what you see is that P intersect Q actually is equal. Intersect Q is equal to Q intersect P, right? Yeah. So you see that there are similar structure here, right?
Yeah.
But you also need to consider all this. You need to consider all of this. So including, so yeah, there's some similarity here. So there's similarity 懂吗？相同 Yeah. So there's some similarity between these two theory. But if you want to, 所以你是想要代替整个东西嘛，对不对？
对，但是我现在不知道那个横杠那个就是因果那个应该怎么在这里来表示。
Yes, that's the problem. Yes, that's the whole point. That's the whole point. That's the whole point. So last time there's one student come and ask me. So I think she think that maybe P have to go inside Q, but it doesn't work with the true false thing. Yeah. So that's why. So if you want, maybe you can try to figure out, this thing how to represent it.
那就可以先把它变成，就是用下面
你第三
这个，然后再是什么？
Yeah. One of the yeah.
先这样，然后在这里。
Yeah. Can try. I think yeah.
所以他们是什么关系呢？是
什么关系？
就是等
you mean set theory and logic 啊？等价 Let me think. I don't know, but seems like it. Wait, let me think. Okay, another thing. Yeah. So when you talk about not P, right? Okay.
not P.
So in set theory, when you do not P, actually you didn't realize you start with another bigger step.
Yeah.
If not, you can't talk about not P. You know.
但是在这个小问题里面，它的全集就是 P 和 Q 的整体。
But now how about this? Not P. you need to interpret this as why it's not P.
非 P 是这个，然后非
Q
P 就是这个。
No. I mean no. In this line here, there's no Q.
所以它的
So
全集
yeah.
不，那这全集就是 P 啊，P 的P 的补集就是空，然后空的补集就是 P，所以就是还是 P
现在换成我不懂了，
啊。
因为我是那些中文词有些不太会。OK， 我懂空集是 empty set。喂，等一下，喂，补集是什么？
就是全集的去掉那
对
一个就是
呀，全集对呀，所以我就说 you need to have a universal set 先啦。
是
So that's why, yeah. So when you how to say? So it's not enough to just look at P and Q. So you actually need to look at a larger set, you know?
但它如果它只有两个，我就可以认为全集就是这个，然后它有一个，我就认为全集是那一个。
全集就是那一个。Then
三个的话，全集就是
wait.
三个加起来。
对，不能，cannot. You see. So you say okay, only got P, so you say P. So not P is empty set, right? Not empty is what? P. But if I Q, not Q is empty. Wait, okay, too fast I got Q. So let's say I got Q, different from P. Not Q is empty. You say not empty is P, then not Q anymore. So not well defined.
但是在这个问题里面，它的全集不就是 Q 了吗？
但是不 well defined 呢？不 well defined 就是 no， 你知道什么叫 well defined 吗？
不知道，
中文是什么？
无法定义。
无法定义。就是 when你换不同的选择的时候 ，you change the choice, then you get different answer， 这是不可以的，在数学里面。你明白吗？你明白吗？
不太明白。
你不太明白。就你看这个例子，你看这个例子，所以你刚才说嘛，
但我觉得这里也应该是 Q 呀，为什么？
对呀，
为什么不是？
这样你的定义就有问题了啊！这样你定义就有问题了，这样你的定义就是有问题啊！如果假设这个是 Q， 你看这个定义就有问题啊！你看这个路线是怎样啊 ？First, I look at P， 我说 not P is empty 吗？因为你刚刚说的嘛。那 not empty 是什么？你要怎么 define？ 那你告诉我。
但是如果你现在引了一个 Q 进来，那 not P 就不是空了呀，它就是这一块。
不能，这两个是活在不同的世界。你讲活在不同的世界，就是
就是它全集不能变化吗？
不是这个问题，就是他的问题是我没有把他们两个放在一起看，就是这个是个体，这是个体，
那我不同的个体就不同的全集有问题，
个体有不同的全集，
有不同个体就不同的全集。
不同的个体有不同的全集，可以没有问题，但是你 not 那个全集肯定是回去相同的空集嘛，你不要跟我说这个空集跟这个空集不一样，对不对？
那可以不一样，
可以不一样吗？
不可以，对，空集就是一样。
暂时不可以，可能你有什么新理论我就不知道了啊，可能你就制造什么平行时空，
所以意思就是两个都是空，但是它们的全集不一样，导致它们非空以后都不一样。但是它们不可能说两个空集
不是导致它们非空之后是一样，但是你要它不一样。对，因为definition 嘛，对吧？如果你说我这个世界有很多空集，可能有可能有空集，可能有可能。
不知道这个什么上周没来。
哦，你上周没来，你上周去哪？
我上周签证没下来。
哦，签证没来。哦，是你是其中一个没那个 email
我没有，但是我加进了某
哦，
个，
你加进了，OK。
就这个符号我不知道别的。
哦，没有。怎么你别的都知道也是？
别的我知道刚。
这个符号是我刚刚教的。这是什么？这个是，这是
我开始就看之前去了。
一开始教啊，这个就我一开始教。这个是今天教啊，是这个。
有开始听不懂，看之前就刚刚就没有。
这个，我指这个是这个，没有写错字。logic 没有写错 ，OK，歪了一点。这一个代表这个，
就是逻辑上完全相等。
对，对。然后我说了什么叫做逻辑相等，就是你要修这个，OK，要修这个也等于修这个，一样的 true values in all possible way，OK，所以你要说他们两个，这个和这个是相同的，这里。这两个要一样，你看 have the same true value，你看一样吗？
一样，这两个一样就会有这个了。
对，
这个就
有哪个？
有这个就有这个。
对，没有错，没有错，没有错。Yeah. Okay, let's come back. Okay. Okay, try. I know maybe sometimes English is a bit hard for you, also hard for me. Okay. So, but we just like try our best to to learn. And this is the only place you can do mistake. If you go out of the world, I mean not go out of the world. This is the end of the world. But if you go out of the university, if you do mistake, then maybe people won't pay you. Okay, first of all, won't pay you. Second of all, maybe they don't forgive you so easily. So this is the place you can make mistake. So just try. Okay. Yeah, just try. Okay. It's okay if you do something wrong, but I can guide you or tell you, share with you something like that. Okay. So the next thing we want to learn is the universal quantification. Okay. Like what I told you. So don't be scared by this word. Okay. What you need to think when I tell you new definition, you just find the keyword first. Okay. For example, in this definition is universal quantification. So just remember this word. No need to think much about it first. So you just think, okay, I got a universal quantification. Okay, is what? So I'm going to tell you is what. So it's a statement for all values of x in the domain px. Okay, then I tell you what is it. Maybe you still don't know what is it. I already tell you what is it. Okay, maybe it's like very obscure. Then I'll give example. So for example, for every x in, should I write in word or? Okay. Let me move this example down. Okay. So let me introduce notation first so that we can write it faster. Okay. So sometimes we will use for every. And then the D I draw like this. I think px. Okay. Usually we will write like this short form, very short form. So it's like for every x in D px. Okay, so you will notice that this is a inverted A. Okay, inverted A. Inverted. You know what's inverted? 倒转. Okay, inverted A. So why is it inverted? Last time they used this tag writer. The tag writer. So they want to introduce new symbol. How? They just pull out the A and then turn it over and then like this. Okay. Because there's no special machine for mathematics. So yeah. Okay, so definition. Oh, also, if you don't understand my English, you should ask me, okay? Don't be blur and then come ask me. I don't know what I teach just now. Ask me if you don't know any English I say. Maybe I said it wrong. Okay, so this A we will call it a universal quantifier. Okay, what else? What else? Okay, so like what I said, there are similar way to say it for every, for all. What else? For any, also can. For any, or maybe given something, it works, everything works. Okay, also can. Okay, so let's do example. Must not miss this example. So for every x in R, okay, real number, just now I give you the example, you should think of what number is inside here now, inside your mind. And then x plus 1 is greater than x. True or false? Huh? Who said false? Who said false this time? Huh? True or false? True. Why true? Say again? Because plus 1. No, you are like not explaining. I was already plus 1 there. So why? Correct? So why 1 bigger than 0 will explain it. Okay, so we all know that 1 is greater than 0. If I add x to both sides, okay, adding x to both sides, we will get this inequality. Okay, makes sense. So this one have to work for all x. So that means I need to pick any x here. Okay. Okay. There's a key here. I want you to notice here. There's a key here. There's a key here. Here, for every x in R, x plus 1 is greater than x. Here, I said take x to be R, x plus 1 greater than x. There's a subtlety here. So this statement here say it works for all x. Okay, every x you put in, it works. Here, what I did is I take one x and I put it in. Okay. In fact, they are equivalent. Okay, these are the same. So later we will do it again in the rules of inference. So to check that for every x word, you need to take every x out and then check it. Okay, and then this is how I do it for this question. This x is arbitrary. Yeah, I write down the word. Okay. Arbitrary is random one. I pick one x and I put it in. Okay. Since it works for any x, so it works for all x. Okay. Jason, any question? So statement. So let's say if you want to check that this is not true, what you need to do? Not true when there is one. You can find one x such that it's wrong, then it is not true. Okay. One x. If you want to show something, this kind of statement is not true. Yeah, remember the last time we talked about the every number greater than 1 is less than million one, the example. So the 2 million is the counter example. Counter example. Okay. Yeah. So next. So next, we want to show that We want to learn existential quantifier. Okay, and then this time, yeah, this time is saying inverted E. It's the proposition. Okay, yes. There exists an element X in the. Not that you see, every time when I talk about an element, I need to say a domain one. So this X need to live in somewhere, okay? Like you need to live in a house. Okay. There's a space that the X live in. Okay. Even if you don't have the house, you also live on the earth. If you are not on the earth, you are in this galaxy. If not in the galaxy, you're in the universe. So there's some space you have to live in. Okay. Let's get px. Okay, notation. Notation. There exists an X in D px. Okay. It's the inverted E. Okay. So when you are in the kindergarten, right, you first write E. Sometimes you write the inverted one, some kid. So actually, there's one symbol for it, inverted E. So this E is called the existential quantifier. Okay, so there are a few ways to say it. There's this. We can find. Okay, we can find. There's this X that works. There's this student. What? The lecturer. What? Okay. Example. Example one. First example. There exists an X in R such that S squared equals to 2. True or false? True or false? Huh? No sound. True or false? True. Why? Why? Why is it true? True or false? Huh? Who say true? Square root 2? Yeah. Okay. True. Take square root 2. Yeah. Very good. Someone asked. Is square root 2 in R? Is it? Yes. So this is the irrational number. Okay. Irrational number is in R. Okay. Yeah. Yeah. About this square root 2, there's a story. Okay. You want to hear story? Huh? Okay. Story you interested? Okay. So square root 2. So in this world, so in the Greeks time, Greeks, Greeks, yeah, Greeks. Okay. So they like about the beauty of mathematics. So at that time, the number system is only up to rational. Okay? Everything can be nicely represented by a ratio. Okay? So okay, I draw here. So they come this problem. Okay? The Greeks like geometry a lot. Okay. So if you know there's a Pythagoras theorem for this, right? So a squared plus b squared equals to c squared. Pythagoras theorem. Okay. Pythagoras theorem. So Pythagoras is a mathematician, and then he got a school. He got a school called, the students are called the Pythagorean. Okay, the Pythagorean. So they are interested on this hypotenuse. What's the length of this hypotenuse? It's square root 2, right? Is it? Geometry. So they want to figure out what number is this. They think that it should be a rational number. In fact, it is not. It is not that someone tell them it's not. And then this Pythagorean, this group of people very angry on him. And then they even kill him. Yeah. Okay. And then then we will learn this proof later. Okay. If not today, next week. Why square root 2 is irrational. Okay. We will learn this proof later. Okay. Very classic proof. The first proof I learned in my pure maths class, or you also see it once in your lifetime. Okay. Yeah, later, next time. Okay. Okay. So actually, there's more answer to it. There's two answers to it. You also can take minus square root 2. Okay. So actually, there are 2x to solve this question. Okay. 2x that solve this question. And then this is the only two. Okay. If you use the algebra, there are only two roots to this function. So okay, this is the 2 1. Okay, let's do the other example. So there exists an x in R such that x squared equals to -1. True or false? Huh? False. Why? Huh? What? Can't hear. Okay, there's no such a number, no x in x squared. It's actually, okay, wait, I will go into complex later, okay? So x squared less than 1, right? So if you square a number, you always get positive number, okay? And then so this, okay, this is another story. So this is another story. Okay, did I write something wrong? Yeah, no x in R such that, oh, 0 0 0, sorry. Okay. Yeah, so this is another story. So the algebraic people are very unhappy. Square S square cannot be negative. So how can I solve this polynomial? So I introduce a root. Call it I square such that +1 equals to 0, which means S square equals to -1. This is how the complex number get introduced. And in fact, this complex number proof it works. I mean, it is very useful in like electricity stuff, application in electricity. Yeah. So like what electronic E and E, they will use a lot of complex number. I think computer science also use it, but I don't have the number. Yeah. Okay. So next. Oh, next. Maybe I just copy. Let me see. Can I copy this chart here? So let me copy this chart. The chart here. Yes. Okay. So if you ever, so this is a summary. So if you have a statement which is the universal quantifier, you want to prove it is true, you need to show for every x. Take one x, show that it's true. Okay, do it for everyone. And then when is it false? You just need to find one such that it is false. There's this px, there's this an x px. You just need to find one is enough. But just now there's one example I found, 2. Okay. To show that it is false, you need to show it is false for every x. So every x you put into px is false. It sounds harder. Actually, it's harder sometimes. Sometimes easier, sometimes harder. Okay. For example, okay, another example. More example coming up. So exercise proof or this proof for every x in, okay, I restrict to positive one, s cubed greater than equal to s squared. I give you 2 minutes to think. You can talk to your friends 2 minutes. Decide true or false, and then how to prove or disprove. You can talk to your friend beside you, behind you. Okay, let's come back. So if I want to show that if it's true, then I have to try every number, right? So let's say I put 0. Okay, 0 greater or equal to 0. Okay, works. X equals 0. Maybe let's try x equal to 2. Okay. 2 is 8. 8 greater than 4. Still true. Maybe true, but don't know. Real number has a lot, infinite members in R. Right. So I don't know. I have to check everyone. Seems hard, right? Okay, maybe I will come back later. Let's say if false. If I want to show that this is false, what do I need to show? I just need to found one number such that what? S cube is less than S squared. Okay, someone suggests 0.5. What is 0.5? Cube 0.5 square. Okay, I think with my calculation is 0.125 and 0.25. Yeah. Okay, so see, you already found one. Okay, so actually it is false. Okay, I can provide. I want to remind you your high school maths. Okay, first of all, I want to do one. Okay, so in your high school, you do something like if you will rearrange it to something like this, right? And then you try to factorize, right? And then you will do, I don't know if you do this table thing or not. 0, 1, 9, and then so on and so on. Or, oh, 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 okay. Yeah, this is a foundation stuff. Actually, I learned from my cousin. He's doing foundation. So, so you need to pick where, so if you want to show it is actually, let me see, less than 0. So you need to pick this area, right? Okay, say 2. So then it will be this area. So actually, all the x in between x such that x in between 1 and 0 works. Okay. Okay. There's another geometric There's another geometry proof. Okay, so geometric proof is to sketch the graph. Of course, to sketch this graph, you need to know the property of it. So S cube is something like this. Right? S cube. S cube something like this. Okay. And then S square is like this. Hey, wait. Better or what? Yeah, better. So this one is higher. And then pass through and then go like this. So actually this line here is like one. Okay. I like geometry, I like algebra. So I like these two. Okay. Yep. So maybe I change the color, make it easier to recognize. So see, we only care about the first quadrant here because we look at R greater or equal to 0. So we're only interested in this quadrant here. Okay. Yeah. So I produce you a geometric proof, algebra proof. In this case. Although this is simple, make sure you understand again. Okay, next. So sometimes existence is not maybe we want a more specific one or more detailed one. Maybe there's only one if and only the unique one. Okay, so we will call this uniqueness quantifier. Okay, there exists a unique element x in the domain such as px. So it's unique, right? So it's unique, exclamation mark, unique. Again, it's a unique one. Unique, okay, maybe unique. Okay, so the unique one, what do we have? Let me see. The unique one. So there exists a unique one. There's exactly one. Exactly one, okay? There's one and only one. Only one. Okay, let's give some example here. Let's see. So there's this unique x such that x minus 2 equal to 7. What is the x? 9. Yes, there's only one x. X equals to 9. So to prove this, you just do the algebra. Right. Okay. So in this case, I can even reduce this question to z only, or reduce to n. Okay. Similar question. Okay. Okay, next. So there exists a unique x such that s squared equal to 3. True or false? True or false? Why? Why? There are two answers. What are the two answers? Square root 3 and square root minus square root 3. False. Okay. So usually these x square have two, like the number of root is the number of the highest power of x. But depend is solvable or not. But anyway. So okay, good. So we can also have De Morgan's law, right? So let me try to move this. Okay. Copy again. Next one. Okay. Let's so there's De Morgan's law for quantifier as well. So if you negate the existence, you need to show for every x, not this is false, not px. So this for every x, ps is false. When is it false? There is a x for which px is true. Huh? Oh, when is the negation true? Wait, let me see. So is it when is the negation true? So the negation, when is this true? For every x, ps is false. When is it false? There's this ps such that there's a ps such that ps is true. Huh? Makes sense or not? Let me write it down. So not every x px. So become there's this x such that not px. Not px is px. So it's like we still use the same logic, but now the logic the proposition has some variable. So when we have some variable, we want to quantify it, whether it's there exists, whether it's for all. Okay. Similarly, if you have a not, if you want to negate for every x px, okay. So to avoid confusion, so this not when we put up here usually mean this. Okay, usually mean this. Okay. So when you bring the negation in, we have we negate for every become there's this, and then we negate this. Negate. Okay. So yeah, you should be able to prove this by using word. Just using word. So it is not the case that for every x px, that means you can find an x such that ps is false. Okay. So when is the negation true? So you negate this again. Let me write it down for the sake of explaining. So you want to dot this. So not exist become every not x. And then again for every x, yes. So see, so you negate the negation, so it's false. So PS is true for every x. Question? 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 No question? Any question? Just ask. If no question, we keep continue again. So let's see. So let's try. So example 1. Not for every x in R, x greater or equal to 0. So what is the negation of this line? Huh? For all become? For all become? What? For all become? Become what? For all become? There's this? Hello? Okay. Only see nothing. So for all become there's this x in R. X not equal to not greater or equal to 0 is s is less than 0. Okay. So I want to make a point here. So this is what? This is not x is greater than or equal to 0. So you see, actually this is two statements here, right? So I let P to be x is greater than 0. And then Q is x is equal to 0. So not P or Q is logically equivalent to not P and not Q. So what is this rule? Huh? What is this rule? De Morgan law. So this is the only law I want you to remember today. De Morgan's law. Okay, so see, you have used this De Morgan's law. Okay, so not P is what? Not P is what? Not P is S is less than or equal. Okay, you can be equal or equal to 0. And S is not equal to 0. So, so, so if X is not equal, okay, see. Okay, see. R or S. Okay, I haven't used S, right? So R or S and not S. Right? Huh? Yes? Yes or not? And then what do you get? Get R. Why you get R? Okay, for those who are wondering, let me write out. X is less than 0. X is equal to 0. Is it R? I don't know. Is it R? Huh? R. Is it R? Okay, this is exercise. Let's exercise. Let's check this. Okay. Check this one. Yeah. Huh? Who are convinced? Huh? Right. Okay, I just use word first. So this is true. Okay. For this statement to be true, either of them have to be true. I already tell you this is false. Then this has to be true. Okay. Okay, this is by word, but you should show it by the truth table. Okay. Okay. What else? What else? Okay, have I done? Done? Okay, done. So I already show you what is not this, right? So you bring the not in for every become there's this, and then you turn this around. Okay, so this is all the detailed thing you should have in your mind. And after you master this, you can just go from here to here. Okay. The next. So what's the second example? Not that exists and x and x. Okay, so what's the negation of this? That exists become what? Huh? What? That exists become what? Become for every okay for every x in z x minus 7 is not equal to 0. Okay. Anyone have question? No question? Okay, since you guys learn about logic, right? This what I wrote is a proposition. So whenever you see it, you want to decide it is true or false. So is this true or false? True or false? Huh? Actually, I don't have answer yet. So false. Why? Huh? If x is 7, okay, take x is 7. 7 minus 7 is 0. Okay, good. How about this? Oh, we haven't tried this. There exists an x in R such that x less than R. True or false? True or false? This line here. True or false? Huh? True. Why? Why? Who? You? Louder. Good. Take x equal to minus 1. Yeah. So you found an x such that x is less than 0. So see, so last time we say that if this statement is true, the original statement, the after the not is false, right? So to show that this is false, you show that this is true, and then this is what you need to show. Okay. See? So now we are putting all the stuff together now. Okay. Yeah. Okay. 4 more minutes. Oh shit. Cannot do the 1.4. Let me see. Can I finish this next week? Oh, actually not too bad. Okay, actually not too bad. So, okay, I want to finish up to rules 1.4, okay? Let me finish 1.4 before we go to tutorial. And then next week we will do proof. If there's no accident, next week we got a quiz. Okay. Week 3, week 3, week 3, right? Okay. Okay. Now I want you to do an exercise, okay? Do this exercise. Proof. Not doing now, okay? Go back and do. Px minus q, and then there's extend px. Okay. Sorry that you have to wait until Thursday because my class until Thursday. So I have to wait until the last class before I post it. So do this exact exercise. Yeah. Okay, you can prove it by word using algebra. Using algebra. Okay. Next. Can take a screenshot. Huh? What? Done? Okay, next. I want to do this and then do the tedious thing and then we will go into tutorial. Okay, next. Okay, this one I want you to know, okay? Sometimes we just not only have one, we have like few variables in our predicate. For example, I want you to learn from this example here. Okay, let us look at x plus y equals to y minus x. So we will have 4 cases in this case. So maybe I swap this one. And then maybe I have this first. And then for every. And then I also have this. Okay, I want you to know this thing, okay? You must know this thing. Okay, so these are your predicate, but I changed your quantifier, and there are two subjects here, okay, X and Y. So these order are very important. They will affect how to read the whole sentence, okay? First, when I speak about X, then X will be fixed, okay? So when I say for every X in R, in your mind, you should think that this X is already occupied by one real number. After that, only you do the Y. Okay, I will give you example. So let's see. So for every X in R, okay, every X in R, so I maybe in my mind I got 2 plus Y equals to Y minus 2. So if I put any Y here, does this work? Huh? Doesn't work. For example, okay, I'm a practical person, so I want to try first. So let's say I try 1. Maybe use 1 plus 2. Okay, now I use different colors so that you can differentiate Y and X again. 2 plus equal to minus 2. So is this true? So 3 is equal to minus 1. Clearly false, right? Right. So in fact, I got a general method to solve this 4 question here. Okay. So first of all, I can rearrange the equation. So it's the algebra method. So what I can do is 2x equals to 0. Okay. And then which means is s equal to 0. Okay. So that means I transform, what happened? I transform, okay, I transform, okay. Okay. Yeah, oh, I know. Okay, yeah. Okay. So I transform the whole sentence become just x equals 0. S equals 0. S equals 0. Okay. So the power of this transform is you can straight away read. This is clearly wrong because this statement is only true for x equal to 0. It doesn't hold true for any other x. Okay. So that means these two are false. Okay. How about for this two case? There exists x. So true, because x can be just take x to be 0. Not sure yet. Not sure yet, right? I need to still consider, is it true for every y? Is it true for every for some y? Okay. So in this question, there's no y involved. So y, I can put any y. Okay. Similarly, if it is true for all y, of course there exists some y. Okay. So both are true. And then one exercise I want you to do is without manipulating this guy, can you just like see this is false from this equation itself? Okay, so exercise what I need to be precise a bit. So exercise, see the truth value of the proposition without modifying first. Okay, although they are equivalent, but I want you to like think more. What time is it? What time for again? Can I finish last 4 slide. Let me finish the last 4 slide again. I don't want to copy. I want to write already. I want to copy. Okay, let me finish this 4 slide before we break for tutorial. Okay. Okay. Otherwise, we are out of syllabus. Okay. So these are some bureaucracy, no, some word you need to learn, but not very important. When you want to discuss stuff, you should know what word you use. So an argument is a sequence of statements. I already told you what is statement, right? Something that's true or false that end with a conclusion. Okay, this conclusion is just some English conclusion. And then an argument is valid if the conclusion is true whenever all the preceding statements are true. Okay. The statement preceding the conclusion are called the premises of the argument. So it's like your argument consists of premise, and then conclusion. Conclusion. And your argument is valid only when you talk about the right conclusion, right? If you say about different conclusion, then your argument not valid, because you're explaining other things, right? Because you are explaining other stuff. So yeah. And then if you have a different incorrect reasoning, these are called the fallacies. Okay, fallacies. Maybe you have some fallacies here and then give you an invalid argument. Okay, these are just some no need to care much, but you need to know this one. And then next, this is very important. This is very, very, very important in the proof. So, like what I said just now, if you have P implies Q is true, and you have P, then you can get your Q. Okay, and then the other thing is if you have P implies Q, you have not Q, and then because this is equivalence to not Q implies not P, so you get not P. Okay, and then this is like transitivity, so you can go from, if you have P to Q, you have Q to R, then you straight away can go from P to R. Okay, and then this exercise just now I asked you to do what? If you have P or Q, and then you have not P, then you must have Q. Otherwise, P or Q is wrong. And then if you have P, and then you can just this is disjunction, is it? Disjunction. So disjunction with anything else, even if it is false, never mind. Because as long as you have one thing is true. And then P and Q both have to be true, so you can just take P out. Okay, this is like if you have both of them, you just need one of the condition, you can just take it out because you have both of them. And then if you have both of them together, then you can have a condition that they are together conjunction. And then what? This one, yeah. You can look at it. This one, not much comment, but why these are true? Actually, you can show that these are from the tautology. This exercise, try at home. Try at home. Okay, these are exercise. Okay, just in particular, just now we use which one? This one. See, tautology. Okay, exercise. Okay, try this. Show them they are the tautology. Very important. You must master the skill. So what? Oh, okay. So let's give this example here. So let's say I define what is 8 and heaven 8. Okay. So not egg is have an egg or have eaten. So not full is hungry. Okay. Let's say I say that if I ate, then I am full. I ate, so I'm full. Okay. But this is different from I am hungry, I'm not full, then I haven't eaten. Okay. These two are not logically equivalent. Like this, like this, like this. No. Okay. Hey, wait. Okay, I think I'm sleepy now. So this is wait. Okay, let me write it down. Okay. So this is P. This is Q. This is not Q. This is not P. But if you say this is not P, this is not Q. Okay, what I want to say is this. Okay, these two are logically equivalent. These two are logically equivalent, which means this two is not logically equivalent. So, like what I said in the beginning of the class, I may be hungry because maybe I'm not because I'm not eaten yet. Maybe I go to sport, so I'm hungry. Okay, so it's not logically equivalent. So this must always remember. So I write down clearly here. So this is logically equivalent to not Q, that's not P, and then not logically equivalent to not Q, that's not Q. What's this called again? So this is called the what? What is this? Wait, let me point out first. This is called the what's the name of this? You sort and then you put two negation. Huh? Contra? Positive. How about this one? Inverse. Okay. Okay, and then another summary. Another summary here. So for every xpx, you can make a deduction that all the x here it works. Okay. If for every cpc, then you can say that every xpx. Yeah. So for example, yeah. So for example, I'll take example here. What's your name? What's your name? Your name? Yi-Tian? Yi-Tian. I don't know how to spell. Can I write? Uh-huh. T-E-Y-T-E-N-G-E. Okay. How about you? Zhang Zhou? Zhou? Okay, let's say I take this. So, Xinghui pass the discrete math. Then Yi-Tian pass the discrete math. And also Zhang Zhou pass the discrete math. And then so on. I check every one of you, every row. Then I can deduce that every student in the Tuesday group passed the discrete math. Okay, so this is what the universal generalization do. Okay, understand? Now you check for everyone and then you say that everyone yes. Okay, and there's this xpx is you can find a c such that PC work. We already showed it already, right? The square root 2 thing. So we have like, and this is 2, 3. We have like square root 2, that square 2, 2. Remember the number? And this is x. We have such that square root 2, 2. Okay. If this is true, then we can find some x such that x squared is 2. So which minus square root 2 is 45. So the logic here, right, is all similar, but whether you read it down or you read it back. Feel like you're more confused. So okay, never mind. Later if you confuse, you ask question again. So let's say the fourth one is if it is true for some x, then you can deduce that there is this one. So if you found this equation here, then you can say that there's this x in R such that S. So it's like going down, going back, going down, going back, going down, going back. Okay. Any question? No? Okay, now we break until 6:15 and then we come back for tutorial.哎，
这个问题，
我
没有太懂为什么这个是2代。
对，
这个要怎样理解？
我这里，我的问题就是要你找
啊，
让你修，
让我说，
对，或者让你证明，
这是对的，
对，如果不对应该是错的，应该要对。
这个怎么证明？
怎么证明？怎么证明？
我需要把这个 R 和 S 换成一种事件吗？还是
没有啊，已经换了，
换成
已经换了
事件了，对吧？
换了，对，已经换了，所以这个应该是要对 for 所有的 R 和 X。
那这个 R 是小于0 ，S 是等于0，它那个
不，对，
如果它是或的话，那它是表示什么意思？它是小于0，它是等于0；或的话就是小于等于0，还是可以小于0。
对啊，你所有你说的东西都是对，
都是对的。那它和这个不是非 S，
对，
这个非 S， 那么就是不等于，
对
，S 不等于，
对。
那他们的这个不就是和吗？
对，
那他们的和不应该是什么？可以小于0，可以大于0。
是交集，三个，
对啊，就是交集，它的交集的话，不就是小于0？是小于等于0，交成一个不等于，所以就是小于0。哎，对，小于0。哎，没问题。
不，我现在要你修的是来in general，就是怎么说？general，对啊，
一个小于0，一个小于
通常我忘了是
我懂，
对吧？常规
一般我懂了。还有一个问题是这个，这个我不知道怎么理解，就是 P 和 True 的交集等于 P，因为我第一节课没有了。
你第一节定义就是，第一节课没有。
P 就是真，P 就是一直是真。对，
它就一直。
那为什么它是一直真的交集？
你就画和 P 啊 ，True 啊 ，True false 嘛，但是对的永远是对的，
对，
然后 P and True 嘛，对，True false，对，这一个跟这个是一样，是吗？他们两个是一样，对不对？
应该是 P。
我懂。意思说，如果你要这个
不理解的话，可以列表格。
不，这个是定义，这个是 by definition，
对
，OK，by definition 是这样，但是如果你要真正去理解它的话，就是说，你和一个对的东西，其实它就永远对嘛，有它没它没有关系。
这个是把它就是去这个是分析它的，但是我感觉这个说你和一个对的东西永远对，这个是对，这个应该是用到这里边，和一个对的东西永远对，是必须用这个
一样啊，对，你
理解的角度不一样。
不，这两个是不同的东西，这两个是不同的东西，这是不同的东西，这个是
这个和这个是或，
对，这两个是不同的，
我知道，
对，
那个或的话才是跟真正的和一个一直正确的东西或，它最后等号后面才一直正
啊，对，OK，对，
你刚刚说反了，你刚刚说第一个的时候，你说和一个正确的东西原来正确， 是。
哦耶
如果它是错误的话，那它这个
耶
它不是
耶，应该是错的。
不是。我觉得刚才你说那个空极它的反面，其实它的空极的补极应该是全极，然后全极是可以变的，所以我觉得没问题。
那如果你这样的话，你不能够因为你的意思 ，OK， 你的意思是全极
就是
都是
集合
P
和
和
命
Q，
题来理解，
就是你看，
就是在不同的命题里面，全极是可以变的呀。全极我记得定义上是，那它如果可以变的话，那就没有。
那应该全极不可以变，全极跟空极是不可以变的，
全极不可以变吗？
不可以，空极和全极就一个，不可以变，
应该是可以的呀，全极
不可以，
不可以。
不可以，所有的极
那
都
像那像那像这种题目里面也会有吗？就比如说这里是实数，然后你把它，然后后面比如说这里不是这个，比如说 x 大于等于0，然后你要把它取一个补记以后就变成 x 小于0，那它的虚数就没考虑。
不，你在
它的那个全集就是 r，就不是那个 u，就不是所有数，它只考虑实数它的全集，是吗？
啊，OK，这个是有一个叫那个，你可以去搜，它是一个 contradiction 叫什么啊中文叫 contradiction，它矛盾，有一个矛盾就是没有一个 set 是可以是它自己，还是
没有一个集合可以是它的，我好像听过这个。
或者是没有一个集合是可以有它自己其中一个，但是你这个做的事情就是那个，
我这个做的是什么？
就是因为你说它就
我只是说全集可以变，然后这样是不是就是这个命题可以和全集就等价了？
问题是这个世界里只有一个空极和全极。
就是每一个问题里它都有一个全集，然后空集确实就
不
是一样的。
不是，就在这个极的那个理论里面，只有一个空极和一个全极。
全集我觉得应该是，就像你这种问题，就我刚才说
再给我
的
想一下，
啊
没有，再给我想一下
啊，
啊，全极可不可以变？
应该可以。那要不然这些问题你都没考虑到。
喂，OK，就算给他变嘛，给他变吧。那我的问题是那个空极也只有一个，
对，空集只有一个，但是它在取补的时候就出现问题了，因为它取补以后是全集，所以它其实是一样的。
OK，再给我想一下。
那空集就是一样的，确实一直都是一样的。但是它是补是不一样，补集那个
感觉是不可以。再给
就是那个
我想一下。OK，给我想一下，给我回去想一下，给我回去想一下。好啊，
好 OK。
还有其他问题？
还有那个字母怎么写？那几个
字母
那个数，就是我感觉老师你写那个 r 这个，就比如说什么实数集、整数集、有理数，就是它的是和 r 不一样，为什么要多一笔？
粗一点的，
粗一点，对，
就粗一点。
然后 c
也是粗
c 是加一笔，那
也是粗一点的。
也是多一点。
那你可以，我是这样啊，但是你可以这样，反正有个 Q 吧，
这是 q 是吗？
呀，Q 应该是这样。哦，或者你这样也可以，这样也可以就粗。
我还没签字吧今天。
可以，还没签字，等一下我要传下去。等一下现在传下去会乱的，等一下我传下去，我忘记
再讲一下，就随便找一个例子，
是说
不是很懂。
OK，这个哈，这个就是其实呢，要想说就是 for every x 的话，OK，你什么不懂？我不知道你懂不懂，
两个都不是很懂，
都不能懂。我想说就是
就找个例子讲一下。
不然你给我一个例子，
就是上面的例子，
就这个例子，好吧？就这个例子。
机器人。
OK，这个是另外一个故事，但是你要理解这一个再看盲点。这一个是说，如果我先把 x 丢进来， 丢进来，然后我再考虑把 y 丢进来，对吗？然后我要问这一个 proposition 是对还是错，对不对？这个就是我在做的事情呢。我先把一个 x 丢进来，因为我要 for every 嘛，你记得吗？如果 every 的话，我就要选一个嘛。OK，我选一个，然后再试下做这个，再选一个，看一下对还是错，然后找到是错，对不对？对吧？对不对？所以那你就要试各种各样的情况，对不对？但是你不可能试完所有的情况嘛，对不对？所以我其实可以把它简化。其实这一个的条件就是等于 x 等于0吧，
一项
这个就比较容易检查了哦。你明白吗？
就是一项，
什么叫以项？
这个和这个不是可以消掉，然后这个移过去就变成2x等于
对
就是这个是，
对对对对对
然后再
对
x 等于
对对对对对，
这个，但是跟这个是矛盾的，它就是错的。就是因为它这只有一种情况，这是所有的 any，
啊，
是这样吗？
不，问题我想说就是你要重新理解这句话，就是 for every x，for every y，x equal to y，x equal to 0。因为刚才我跟你说的是你要试完所有的号码嘛，那你不可能做这件事情，这么多号码。那你能够先把它简化成这个 x 等于0，那 x 等于0的话，你就可以检查了，明白吗？可以吗？嗯，
那个 x 就代入它等于0的这个情况，这个
就这个啊哈，如果你要 x 等于0，对于 x 能够等于0啊，y 等于 y 是什么意思？我先问你，y 是自由，y is free，我什么 y 放进去，因为它这句话跟 y 没关系，所以什么 y 都可以，你明白吗？明白吗？你不明白？不明白？不明白？比如说 y equals to r 2。OK，二应该不是一个地址啊。OK，放这个啊。For every y in R，2加2等于4。
这个的时候特
这
别
一句话没有 y 在里面了。那我问你，这整句话对还是错？
这个
我问你，这整句话是对还是错？
对，
为什么？后面是对的，然后我取 y 等于1，跟这个有关系吗？没有改变吗？取 y 等于2有改变吗？没有吗？跟这个一样，可以吗？OK，
对，好像有点学长。
OK，啊，OK，OK， so I pass down this attendance sheet and this, and then you can sign and then give back to me. Okay, I think I see a lot of confusing faces. I'm not sure. Okay, different people have different confusions. So I only can ask you to ask questions every time you are confused. Don't wait. If you accumulate, then there's more thing you need to fix. So I'll give you time to think and then try come up with questions and then what? and then come to my office hour if you need help. Let me see what's the tutorial question. Yeah, so the style is like this. So there's a lot of like small thing. Sometimes in classes, you need to believe me first, and then you go back and check. Eh, why like this? Maybe go through row easier. Finish each row and then pass to the other or column. Yep. Let's see. Okay, maybe don't have time for you to discuss. Maybe if you try, then we can check answer. This page. What? Okay. Yeah. So only one thing I can say. So just ask question. Okay. I don't know where is your confusion sometimes. Just ask. Okay. Anytime you can stop me. Okay? If you're confused, you stop me. Don't be shy. Okay? The only solution is don't be shy. Okay. 1.3.2. So in the class, sometimes if I'm using something that I haven't proved, you should accept first, and then you go back and check whether it's true or not. But yeah, okay. So show that not P and P are logically equivalent. Okay, this one I said just now. So you do P, not P, not P. Okay, you see that they are the same. Okay. Okay. Next. Hey, where's your other friend? Where's the friend? Huh? Behind? Two call. Okay. Okay, next. So okay, 1.3.10 talk about they don't want you to write implication, they want you to write this conjunction and disjunction form. So you can do the algebra. Okay. So do the algebra. And then it's better that if you can state what step you have used. Okay. Yeah. Any question now? I'm not expecting you to like straight away do it, right? You have to try. Okay. Okay, next. Show that P or Q and not P or R implies Q or R. Okay, so you just do it's a tautology. So you have to show that this column is all true. How many variable? 3 variable. So 2 times 2 to the power 3. So you have 8 possibilities. Okay, and then you check. Okay. Show that something is tautology or contradiction is a skill you have to master in this class. Okay. Okay. Yes. Okay, I think this one we can discuss a bit. Anyone try this yet? Huh? Anyone try this yet? So the question asks about s in the integer such that x plus 1 is greater than 2x. So it asks about q0 is true or not. So 0 put inside here, 0 plus 1 is greater than 0. So it is true. Okay, q minus 1. So So actually, I should say that Qx is equal to x plus. Okay, so x plus 1 greater than 2x, and then x1 is 2 greater than 2, which is false. And then it says that there exists an x such that Qx. Is it true? Can you find an x such that Qx? I said can. Why can? Just take all the x which is less than or equal to 0. Okay. One way to do this, okay. One way to do this, maybe you want to try number. Maybe you try x equals 0. So you get 1 greater than 0, which is what you want. But if I do through the algebra method, then I can find a lot of x instead of just trying. Okay. So I would say this method is algebra method. And then this one is by try and error. Okay. Yeah. Sometimes you can try and error, sometimes algebra is more efficient. For every x, qx. Yeah. For every x that this is true, I say it is false. Why? Because I can take x equal to 1. What do you get? 2 is greater than 2. Or if I use the algebraic method, -1 is greater than -1. So these are different ways to view a problem. Yeah. And then the next one, there exists an x not qx. Okay. This is true. I said true. Why? I have to convince you. So I take x equal to 1. Similar, 2 greater than 2, false. Okay. This is similar to which question? The reason is the same, but depends on what you say is true or false. For every x, this is not true. Okay, I said false. Why? I just take an example to show you, such that this is true. So when you put x equal to 0, you get 1 greater than 0, which is true. Okay, try digest this. Ask me question. You pick one of the can. Any question or not? Let me think. Everyone okay? Okay with the example? Okay. Okay, this row okay? This row okay? Okay. Actually, I have one question. So every student have to take BM, is it? But some you. Huh? Only international student? So international student have to take. Huh? So international students have to take Bahasa Melayu. Is it? Like the Malay language. Oh, so what guys you learn? What thing you learn in the class? Pronunciation, suku kata. Suku kata is it? How you call it, huh? Taught in Malay or taught in English? Taught in English. English, right? So what kind of word you have learned in the class? Huh? Can't remember. Huh? What word you learn in? Huh? What? No. Can't remember. Okay, this time share with me like what word you have learned. Yeah. Okay. Okay, if not, then we go to the next one. 1.4.36. So you want to negate the statement here. For every x is less than -2 and x is less than 3. Okay, so negate for every you get there's this, right? So there's this, negate this, a conjunctions proposition. What law you use? Huh? What law you use? Negating a compound proposition with a conjunction. What law you use? Huh? What law? What law? De Morgan's law, right? The only law you need to remember today. De Morgan's law. Okay, and then you take the negation of the first one, the second one. And then negate for every x is in between 5 and 0. Okay, so negate for every you have there's this. Okay, and then this is an n proposition. So okay, I can rewrite this as x 0 n x. And then you use De Morgan's law again. Okay, n become O, and then you negate the statement here, and then you negate this statement here. Okay, makes sense? And then similarly, well, there's this become for every, and then n become O. Okay. D for every x is less than or equal to -5, or less is greater or equal to -1. Okay. Any question for this part here? No question? No question. I'll skip to the next question here. Okay, 1.4.52. Have you read about the question yet? Can someone read the question for me? Didn't copy the question. What's the question for 1.4.52? Can someone read the question? 1.4.52. What's the question? What's the question? 1.4.52. What's the question? So that every p like this, or every x, you need bracket or not? No. Every x what? P. every x px or every okay, every x px or every x qx are not equivalent to for every x px or qx. Okay, thank you very much. So you want to show this, so that means you want to come up with an example such that this is not true. Any answer or not? Anyone try it? Not yet? Try. Someone try at home or not? So you want to show that for every x px, if it is true on both sides, I mean, you need to find some statement which is false on the other side. But this p and q have to be the same, right? Okay. Okay, so what I did is I do this. So for every x, okay, my px is x is less than or equal to 0, which is non-positive, or s is greater than 0, right? So for every x, it is either less than or equal to 0 or greater than 0. But if you split them out, these two statements are false. These two statements are false. Okay. Why? Why is it false? Let's say I write px, this one is qx. For every x px, for every x qx. For every x px, is it false? False or not? False. Why? One. So there's this x which is equal to 1. 1 is greater than 0. How about this? Why? Negative 1. So there's this hey, what am I writing? So this is equal to 1. So there's this x which is equal to minus 1, such that minus 1 is less than 2. Okay. And you also can use the integer, so maybe split the integer into odd or even. Yeah. Okay. And then the next one, 1.5.4. So 1.5.4 is just translating English to the statement from symbol into English. So you should try it. Just try it. Nothing to say about this thing. Okay. 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 1.5.2 is more interesting bit. So want to show that okay, every statement whether it's true or false. Okay, we can do it together. So okay, so this is the example of nested quantifier. Okay. So for every x, there is this y such that x squared equals to y. So for every x you put in, you can definitely find y such that this is true. Okay. Hey, are you given the domain of discourse or not? 1.5.2, are you given domain of discourse or not? For you to determine. Forget to copy the question. Is it true for all R or you need to pick R? 1.5.28. Okay. So your domain, your variables are all living in R. So fix R, okay? X and Y. Okay. So first, true or false? True. Why? Why true? Why true? So how to show this? So for every X, you need to find me a Y. So what Y you take? Take Y to be? No, cannot. It has to be true for all X, right? So let's say, give example, you say take Y equals to 1. 1 only work for X equal to plus minus 1. So it doesn't work for all X. So it's wrong. So this Y is wrong. Okay. You need to have a Y that works for all X. Okay. So Y should be depending on X. Okay. X is a function. Y is a function of X. Okay. Y have to be a function of X. So what Y you can take? You want Y to be what? See the question. You want Y to be X squared. So you just take Y to be X squared. Okay. And then what you need to check is maybe whether S squared is in R or not. But R is closed under multiplication. So that means when you take 2R multiply together, you still get a real number. Okay, to be precise. Understand or not? Understand this example? If not, you have to ask them. Okay. B, for every X, there exists a Y such that S equal to Y squared. Okay, true or false? False. Why? What negative? Okay, you say when X is negative, you can't find Y. Right. So like Y negative, maybe for example, Y equals to -2. And this is already a complex number, which is not in real. Okay. Okay. Next, so C, there's this an X for every Y, XY equals 0. True or false? True or false? True. Why? Why is it true? You need to find me the X first. X equal to what? X equals 0. Then if every Y like 1, 2, 3, 0.3, okay, every Y X dot Y is 0 because 0 dot Y is 0. Okay. D, there's this X, there's this Y such that S plus Y is not equal to Y plus X. So what is this? This is the commutativity. So because real number is commutative. So it can't be the case there is some x and y such that x plus y not equal to y plus x. Okay. So the reason is the addition of real number is commutative. Okay. You can't find x and y such that this is true. Okay, next. So for every x, if x is not equal to 0, then there exists y such that sy equals 0 and sy equals to 1. True or false? Huh? True or false? Think first. True. Someone said true. Why? So if it is true, that's mean I give you an x which is not equal to 0. You need to give me y. Huh? Y equals to 1 over x. So usually how I find this, okay, the technique to find this, right, is to look at this equation here closely. Okay, look at here closely. So xy equals 1 imply y equals to 1 over x. So when does what 1 over x exist? Is when x is not equal to 0. Okay, and your condition is x not equal to 0. Okay, make sense? Next, there exists s for every y such that y is not equal to 0 implies sy equal to 1. True or false? True or false? True or false? There's this x for every y. So you need to find an x if you want to show it is true. Then you need to find an x such that for every y it is true. So let's try. Okay, let's try. So my first try is like there's this x, right? I just try 2 maybe. 2y equals to 1. Y equals to half. 3y equals to 1. Y equals to 1/3. So you see, so whenever you change this x here, y is keep changing. Okay. Let's say we try x equal to 0, right? X equal to 0. And then what do I get? Oh, I don't get. I get 0 equal to 1, which is contradiction. Because 0 not equal to 1. So this is not the case. So if you try all the other number, you'll see that it doesn't work for all y. Y are fixed, right? So in fact, this is the idea to show you that this might be false. So to show that this is false, you need to show that for every x, there exists a y such that this is true, but this is not true. Right? You remember? Not P implies Q is P and not Q. This is the logical equivalence ratio. Okay. And this one. Let's see. This one. Put negation. Okay. So for every x, I need to find a y such that this is not true. So I get x times 2 over x equal to 2 instead of 1. Not equal to 1. Okay? There's some room here. I also can take y equals to 3 over x. Or I can take y equals to 1000 over x. Okay? These are, when you do this computation here, it is not equal to 1. Okay? So there are a few ways to show it. Okay, next. For every x, there's this y such that x plus y equals to 1. True or false? True. Okay, why? You fix this x and then you change the y, and then this is your y. So this is y that works for x. Okay, next h. There's this x, there's this y such that this and this is true. So you just need to find an x and y that works. So like what I said, so this part here is very important. So first manipulate this part here. Like here, we manipulate it. Here we also manipulate it first. Okay, so we do the simultaneous equation. So what we get is actually 0 equal to 1. So it can't be true. So what you can't put any x and y such that this thing holds. Okay, because it is a contradiction. Okay, so this is false. H is false. Okay, and then next, so for every x, there is a y such that this and this is true. Similarly, like what I said, this part is important. We can manipulate it first. And then we found that s equals to 1. It's like like what we did just now, we showed that s equals to 0. So this means that only x equals to 1 works. Okay, so it doesn't work for every x. Only works for s equals to 1. Okay. But if I change the equation to there exists an x for every y, then it is true. Okay. X is 1. And then the equation doesn't depend on y. Okay. And then the next, for every x, for every y, there exists a z. Okay. Such that this is true. So this is true. Because just take this to be just take z to be x plus y over 2, because r is closed under addition and also multiplied by 1/2. We call it a scalar multiplication. Scalar multiplication by 1/2. So addition for is so r is closed under addition. The addition of x plus y followed by scalar multiplication and then over again. Okay. So where's the attendance list now? Oh, done. Okay. Later pass back to me. Okay, before we leave, any more question? Any more question? Last question. Last. I will check and then get back to you next time. Any more question? If not, we can dismiss for today.